In this video, I will present the first part of our proof. Briefly speaking, we prove that for such E, if it is a critical point of some functional, the free energy functional, among admissible variation, psi T, which preserve the volume, then we can derive that if we say this guy to be M, then the regular part of M inside is of constant mean curvature, and the regular part of M near the boundary has a constant contact angle. Say this is the unit conormal of M, and this is the unit conormal of B plus. This is B plus. Then the angle between these two unit conormal, theta, must be a constant angle. Let's start our proof. As we previously talked about, such E is a critical point of some functional among admissible variation. So the point is that we should construct an admissible variation. And let's start from some initial variation. An initial variation, doesn't preserve the volume in a short time, but will preserve the volume at the first order, which means that the first derivative of the volume is zero, but the second derivative of the volume fails to be zero, so it doesn't preserve the volume in a short time. And we take X to be any smooth vector field with compact support, and satisfying that the integration of X dot with nu M over M vanishes, and X is tangent to the boundary. The existence of such vector field can be obtained by solving the Cauchy's problem, and we simply set ET to be the image of E under psi T, and we set VT to be the volume of ET. Then, using the first variation formula and divergence theorem, we can see that such X is indeed preserve the volume at first order, but fails to preserve the volume in a short time. And now, for such initial variation X, we want to do some modification to obtain some admissible variation. We do it by writing it as a local graph. Precisely, if this is our omega, this is our M. M could have some singular point. We do the modification near a regular point X. By regularity, the boundary of E near this regular point can be written as a local graph of some smooth function or some C2 function. For example, this is D prime, which is a domain in Rn-1, and partial E is this guy. Partial E can be written as a local graph U0. So this is X prime U0, X prime. But partial E is a graph. Now, since our choice of X is a smooth vector field, so we can find a very small time t, such that not only the boundary of E, partial E, but also any boundary of ET can be written as a local graph. And we denote it by a smooth function U, which is defined over D prime times the small interval For example, we can write this to be U T1, and this is U T2, where T1 and T2 are in this small interval, and this is partial ET1, and this is partial ET2. This is partial ET1, and this is partial ET2. They can be written as a graph of this function U. Now, with this symbol, we can do the modification. Let's consider some smooth function g, which is also defined over d prime and has a time variable. And satisfying that the integration of g over d prime is this guy. And moreover, we want that g has 0 value at the boundary for any t. And for such g, we can define our new sets e to the t by replacing the original boundary partial et, which is given by x prime u here, x prime u, to be the new boundary denoted by partial e to the t and given by we plus t squared times g to the original boundary. For example, this is our original boundary, and we plus some g such that the difference of this guy and this guy is t squared g. And now we have the new boundary. And the advantages of considering local graph is that the volume of the graph is easy to write. For example, this is our d prime, and we have a graph function over d prime, say u. Then the volume of this guy is simply the integration of u over d prime. So we will have the difference of the volume, the new set's volume minus the original set's volume is given by the integration of the graph function, new graph function, minus the integration of the original graph function, which is t squared times the integration of g. And that's why we define g to be this, because we can plug in this to see that the difference of the volume is indeed V0 minus Vt. So we will finally have that the V to the t is always V0, which means that the volume of e to the t is always the same with the original set E. So e to the t is indeed admissible sets. And now we have the admissible sets. And another advantage of using local graph is that the surface area is easy to compute. Again, this is E, this is D prime, and this is U. Then the surface area of U can be easily computed by the integration of the square root of 1 plus the gradient square of the graph function. And now we have the following. The difference of the free energy at t is the difference of the free energy restricted to T prime, since we only do modification inside D prime and outside ET and E theta T coincide. And since D prime is inside, so the free energy's boundary term is indeed the same thing. So we only have to consider the inside parameter at D prime, which is the surface area. And by local graph, we can easily compute the surface area. That's there indeed this. And from this, we can derive that the first derivative of the difference of the free energy is 0. This is because we have t squared here. If we take first derivative of t squared, we will have some term like t times something, and we take and we evaluate at 0. So this guy always vanishes, and we will have that this holds. And since E is stationary, that for any admissible sets, the free energy's first derivative must be 0, which means that the original set's free energy's first derivative is also 0. And finally, we can use the first variation of parameter of E to derive the following holds for any initial velocity x, which means that x is tangent to the boundary and x, the integration of this is 0. And for such formula, we have a standard approach. We will always decompose x to the tangential part with respect to m, and normal part with respect to m. And for the normal part, the tangential divergence of the normal part will give us the mean curvature. And for the tangential part, we can use the divergence theorem. For example, if this is m, this is b plus, and we can use the divergence theorem to see that the integration of this is the integration of x dot with the conormal nu gamma m, integrate over the boundary. And for b plus, it's the same. And combining all this together, and back to this formula, we will have the first variation formula in our case, that this holds for any initial velocity x. And from this first variation formula, we want to derive the geometric information. Let's first deal with the interior CMC. Now we take any x with compact support inside omega, and with the integration vanishes. It is apparent that x is admissible because x is automatically tangent to the boundary. So we can use this formula to test x. And since x is 0 at the boundary, so this guy is 0. And we have this formula holds for any such x. And from this, we will derive that h must be constant throughout the regular part of m inside omega. This is a canonical approach, and we refer to Francisco Madrid's book, Sets of Finite Parameter. Yes. And now we derive the constant contact angle near the boundary. Let's back to this formula first. We now know that h is constant, so we can take it outside the integration. And for any initial velocity x, integration of x dot with the normal nu m is 0, which means this guy is 0. So we just have to consider this holds for any admissible initial velocity x. And we claim that this holds for not only initial velocity, but for any x0 with compact support and tangent to the boundary. And to prove this claim, we simply notice that for any such x0, there exists another smooth vector field with compact support S0, such that if we use S0 plus a constant S times x0, this guy is admissible. I think it should be written as there exists S0 and a constant S, such that this combination is admissible. And this is apparent because this guy is tangent to the boundary. Since S0 has compact support, and so it is 0 at the boundary, and x0 is tangent to the boundary. So this combination is tangent to the boundary. And for the integration, we have, we want to check that S0 plus x times x0 dot with nu m is 0. And since our choice of x, of the constant s and the smooth vector field S0 is for this purpose, so we can always find such S0 and S to satisfy the second condition. So we can use this to test this formula, since it is admissible. And back to this formula, we see that S0 plus S times x0 dot with this guy integration is 0. And since S0 is with compact support, so at the boundary S0 is 0. And for this constant S, we can take it outside the integration. So we finally see that this formula holds for any S x0 with compact support and tangent to the boundary. Now we see that this is a small observation that the integration of x0 dot with nu gamma m is this guy. This is the orthogonal projection of nu gamma m to nu gamma b plus, and since x0 is tangent to the boundary, so the inner product of this guy is indeed the inner product of x0 with the orthogonal projection of nu gamma m to nu gamma b plus. This is the orthogonal projection. So back to this formula. We will see that the following formula holds for any x0 with compact support and tangent to the boundary. And one step further, we say that this formula holds for not only x0, which is tangent to the boundary, but also any x with compact support, not necessarily tangent to the boundary. This is because that for any such x, it can be written as tangential part and normal part with respect to the boundary of omega. For example, this is x, and this is the normal part of x, and this is the tangential part of x. And for the normal part of x, we will see that this formula holds automatically because the normal part of x is normal to nu gamma b plus. So this integration must be 0. And for the tangential part of x, we have this formula. And x tangential is tangent to the boundary, so we have this formula holds. Which means that for x tangential and x normal, we have this formula. So this shows that this formula holds for any x with compact support and smooth. And finally, by the fundamental lemma of the calculus of variations, we have this guy must be identically 0. And this means the unit conormal, the angle between the unit conormals is constant. So this completes the first part of our proof.